299,792,458. A jumble of numbers, somewhat close to 300 million. But that jumble of numbers is not just any jumble of numbers. It is the speed of light. It is a value so integral to the makeup of the universe, the building blocks of the universe, the way it functions, that every scientist, everyone basically knows the speed of light by heart. But is the speed of light actually this very specific number, or can it fluctuate? Can it change? Can it evolve by its circumstances? Well, the answer... In ancient times, many scientists and philosophers, two fields that often went hand in hand, believed that the speed of light was infinite. Galileo was the first to try to disprove that, being the pesky, rebellious teenager he was against the church. He tried to measure it by getting him and an assistant to stand a while away from each other. One lifted up the shutter to a lantern, the other, when they saw the lamp, would raise their own shutter. Galileo then recorded that time, and found, with this simple but ineffective way of measurement, that the speed of light, if not instantaneous, is extraordinarily rapid, end quotes. Concluded that the speed of light must be 10 times the speed of sound, which is 343 meters per second, meaning that he thought that the speed of light would be a puny 3,430 meters per second. Fun fact, by the way, Galileo's father, Vincenzo, revolutionized music theory and upended thousands of years of teaching, which went back all the way to Ptolemy, changing ideas about acoustics and dissonance. This might have been a big influence on what made Galileo so different, as he learned what he knew about the scientific method and such because of his father. Anyways, the first person to try to measure in a somewhat reasonable way was Ole Roemer, who used the newfound information by the man himself, Galileo, about Jupiter and its moons using a form of geometry that I'm too smart for, even with the limited knowledge of where the planets and their moons were. He found that Jupiter's eclipses and its moons were a while off of when they were supposed to happen. He predicted that the speed of light was 214 million meters per second, which is a good guess, as previously stated, the knowledge of where everything was not amazing. Hey, how'd that get there? Well, I guess you should do what it says, or... Anyways, back onto our discussion about goats. The first time the planets and sun were not used to measure the speed of light, other than Galileo's unsuccessful one, was in 1849 by Armand Fizeau. He beamed a light to a rapidly rotating tooth wheel and sped it up until he was able to observe that it took the light a tooth to get out of the wheel. We know that he got a figure of 315 million meters per second, closer than Ole, but is still a little over the mark. Leo Foucault, which is a French name, and I don't know how to pronounce it, I'm sorry, got a very close figure of 298 million meters per second using rotating mirrors, the closest one yet. Calculations and experiments got closer and closer with time. A big breakthrough came with Maxwell's study of electromagnetism, which allows scientists to predict the speed of light in a more indirect way, using the electric and magnetic fields of a space. With this method and the collective brains of many incredible scientists, the speed of light got closer and closer to what we know it as today, 299,792,500, and finally down to 299,792,458 in 1970. Where it rests today. But as to that original question, that one at the beginning of the video, but is the speed of light actually this very specific number, or can it fluctuate? Can it change? Can it evolve by its circumstances? Yes, the speed of light changes. The number that we know so well, that 299 million one, is only the speed of light in a vacuum, or an empty void devoid of matter. Through other mediums, such as air, it has to go slower because it keeps on bumping into atoms. The speed of light in air is 299,702,547 meters per second, just barely under it, but still there is a noticeable difference. Through water, it's 225 million, and through glass, all the way down to 200 million. This means that the number that we've been referring to all this time, this principal factor to the equation of the universe, is somewhat not as defined as it seems. FTL, faster than light travel. According to general relativity, this shouldn't be possible. It says the speed of light is the barrier of speed in the universe for matter. How could we possibly get past this menacing limit? But as said before, the speed of light is not always what it seems. There are a lot of hypothetical methods that have been proposed by scientists, varying in quality from some dumb thing posted on an online forum to mathematically backed wildfire ideas made by physicists. But in all of these, people try to find a loophole, something that general relativity, or the idea that nothing made of matter can go faster than the speed of light, allows through. The first one of these is the idea of a wormhole. A wormhole is basically what it sounds like. It is a hole in space-time, a shortcut. Think of a piece of paper. Usually, to get to one side of the piece of paper, you have to go all the way across. A wormhole instead bends the fabric of space-time, or in this case, the paper, and puts it so that it is required to only go through the tiny little distance between the points. With this concept, it is theoretically possible to adhere to the rules of general relativity, connect billions of light years apart in a few meters. Unfortunately for this theory, it's pretty far-fetched. We've thought of some ways making use of negative matter, which we don't think exists, connecting black and white holes, we don't think white holes exist, and using cosmic strings, which are little defects in the universe that might have formed very soon on in its lifetime. But for that, we would probably have to tie the two strings together, make them vibrate in such a way that emulates negative matter, the thing that I just said that didn't exist. With all of those possible methods considered, it is very understandable to realize that we would need a whole new breed of science to make this idea a reality. Alcubierre drives. This incredible idea is somewhat clean out of a far future sci-fi book. The original idea was proposed by physicist Michael Alcubierre in a 1994 article. In between the complicated mathematics arises a basic idea that instead of speeding up matter to the speed of light, it would instead speed up the actual space-time that the matter rests in, therefore technically not breaching Einstein's laws, which says that the matter cannot go past the speed of light, but nothing about space-time itself. It would speed up behind and before the speed of light, but in the middle it would be perfectly normal. Their speedometers would read the same as when they had started off on their journey. It sounds too good to be true, and this is the case because other physicists have found many problems with it. One of the more glaring ones is that it would destroy all the planets that it passed and probably create a black hole where it ended up. But if we found a way past only planets that we perhaps didn't care about, and we somehow found a way not to create a black hole, which is a little bit of a problem because it would probably suck the ship in and we'd all die, we would still have to find a way to power it, which would take either exotic or negative energy, two things that we don't really think are a thing or just aren't possible. And on top of that, there are some underlying problems with what quantum mechanics and such might do to it, as quantum mechanics might interfere with general relativity in some ways that would make this impossible. Again, another very difficult thing to make a reality. This last way to go faster than light might not be a viable option as to how to exceed the speed of light, but it is one of many examples of particles on an atomic level going faster than this barrier. This example is quantum tunneling, a phenomenon that happens when the wave of a particle goes through the electrical field of another object. It is pretty much teleportation, but instead of the sci-fi teleportation that you would see in Star Trek, it is based in science, very convoluted and confusing science, but science nevertheless. It's insanely rare, though. The chance of you tunneling through a wall, for example, is lower than the whole lifetime of the universe. What makes this already amazing concept more amazing is that this crazily rare thing to happens all the time inside of transistors, which are parts of everyday computers and phones. They're plagued by problems due to their electrons bypassing the electrical barriers that separate them. Quantum tunneling is an incredible phenomenon that shows how amazing the universe and quantum mechanics can be. Thalassaphobia, the fear of the ocean, the fear of drowning. People with thalassaphobia look at the looming depths of the oceans, the enormous size, the darkness, with a sense of unease, a sense of how our puny little human bodies are compared to the vast size of the mighty body of unending void, unending abyss, nothingness, emptiness, chasm, this otherworldly dimension on our own planet, this untouchable thing for most of us, something that we might be able to touch, swimming, diving, traveling on a boat, but we can never truly feel the size, the deadly scale of the ocean. We will never be able to understand how empty it is, how water for miles upon miles is nothing but an expanse of landmarkless territory. I can understand people with thalassaphobia. The ocean is something humans are very ill-equipped for. We have little ability to withstand pressure, or to swim for long, or to breathe. When a person with thalassaphobia sees this picture, they see the image of death, the image of drowning. They imagine themselves in a bad position, struggling for air. When a person with thalassaphobia looks at this picture of the deep sea, they look at the loneliness of it all. They feel the pressure weighing down on them. They see the darkness, the absence of any light. They know that light to humans is incredibly important, something we cannot live without. It is something that we have tried to measure, try to define, and try to beat. But light is a principal part of our lives, our driving energy, our compass, and we are far away from unlocking what it means. But we do know that it is more than a number. It is more than 299,792,458. And as always, see ya.